Hello guys, welcome to Ramta Solutions. Welcome to another lesson on graphs that you encounter in vertical projectile motion in one dimension. So today we are looking at velocity versus time graphs. Okay, today we are looking at velocity versus, no man, we are looking at position versus time graphs. Okay, so these kinds of graphs, you guys remember in our previous video, which was the introduction, the one on velocity versus time, we said position versus time comes from the equation. Let me write it in this color. V delta y equals vi delta t plus half a delta t squared. Remember I said to you these are vector quantities, so it's okay to have something like this. Okay, so I also said to you guys that this thing represents a straight line, a parabola. Basically will have y equals to b, okay, y equals to bx plus ax squared. This was a parabola which can be smiling or can be frowning. Okay, now this expression that you see here, it is basically one where the reference point has been chosen to be the point of release of an object. Okay, has been chosen to be the point of release of an object. Okay, so we are going to look at cases like we did in the cases like we did in the velocity versus time. So first, let's look at case one, which is when the object is dropped. Okay, let's look at case where an object is dropped. So here initial velocity is 0. Okay, initial velocity is 0. Guys, I want you to think of this case, especially position versus time. I want you guys to think of them in this way. Whoever who is throwing the projectile is maybe on top of a hill or on top of a building or wherever, as long as that person is not on the ground. Okay, as long as that person is not on the ground. All right, so I want you guys to think of it in this way. Let's say this is Lesego. I hope you guys permit me to draw Lesego like this. This is the ground, right? And Lesego is here. Sorry, let me make it. Okay, let me make it like this then. Let me make it like this. Let me move Lesego to here. So Lesego is here and he decides to throw the object down, right? So when he decides to throw an object down, when we want to draw position versus time, we have two reference points. We have the ground and we have top of the hill. Let me say hilltop, right? So we have the ground or we have hilltop that we can use as reference point. So this expression here tells you that basically we are taking the hilltop as the reference point. Okay, so I'm going to look at these things in different ways. Okay, so it'll be an extended lesson. Sure, it'll be long. So all right, let's do this. Case one, let's look at when a reference point is, I'm gonna say hilltop. Okay, reference point is hilltop. So now when the reference point is hilltop, what you're going to have is, again, let me choose upwards is positive and downwards is positive. So upwards is positive and downwards is positive. So when upwards is positive, we said initial velocity is 0 because the object was dropped, right? Initial velocity is 0 because the object was dropped. Acceleration will always be negative 9,8 because it is opposite the direction we chose to be positive. Here, initial velocity again is 0, but acceleration constant will be positive 9.8. Right, it'll be positive 9.8. Therefore, our delta y will be half minus, maybe let me remind you, it'll be, remember we dealt with vi delta t plus half a delta t squared. So we will have 0 times delta t plus half negative 9,8 delta t squared. Sorry about that. So this would be 4,9, I believe. So negative 4,9 delta t squared. Now here again equals vi delta t plus half a delta t squared. This would be 0 times delta t plus half into 9,8 delta t squared. This would be 4,9 delta t squared. Now this is a negative parabola, so it must be frowning. This one is a positive parabola, it must be smiling. We said the reference is the hill top, right? We said the reference is the hill top. The reference is the hill top. Wow. Now this one will be something else. Okay, guys, this one will be something else. So you then need to ask yourself a question. If you were doing what is this? If you were drawing this graph in your maths, if you were drawing this graph in your maths, how would it be? How would it be? Let me say this is y-axis, this is t-axis, and this is 0. If you are drawing this graph in your maths, how would it be? Oh my, oh my, oh my. Yes, it would be like this. Now think of it in this way. I'm quickly going to go to the table form of my calculator, and I'm gonna take one. I'm gonna take on my table form. I'm gonna take table. My f of x is negative 4,9. Okay, my f of x is negative 4,9 x squared. Okay, negative 4,9 alpha x squared, and g of x, I don't have it. And then where do I start? I want to start at 0. Okay, I want to start at 0. Where do I end? Let me end at 5, and then my step will be 1. It's okay. So when you look at it, when when you have 0, check this out. When you have 0, something that I want you to see is this as well. You will not have the negative, you will not have this part here, right? You will not have this part here. So you will start at 0. If you have done the table form on your calculator, you will start at 0 like this, right? And then your graph will be moving like this, right? The graph will be moving like this, where this time here will be the time to reach maximum height, while this one here, not the time to reach maximum height, will be the time to hit the ground, where this one here will be the position of the graph below the hilltop. Okay, will be the position of the graph below the hilltop. Can you guys see that? Remember, your parabola, the one that you had on the negative x-axis, on the negative y-axis. Otherwise, you can see that on your calculator. If you did the table, if you went to your table, you can see you had for negative 4,9, 19.6, and all that, right? Good. Now let's try with this one here. I'm going to start here, t-axis and y-axis. So again, with this one, if you go back to your f of x, now make it positive. When you look at this graph, it says to me, it hasn't shifted. So it says to me, I will be focusing on this part here. Okay, I will be focusing on this part here. So if you go to your calculator and say positive 4,9, you will realize that your graph is now moving like this, right? Where this is the time at which the object will be hitting the ground, and this will be the position of the graph, of the ground. Okay, the position of the ground below what? Below the hilltop. Remember, this is the hilltop, which is your reference point. Hilltop, which is your reference point. So this is the point here. If we are to find the point here, it will be what? It will be the position, the height of the hilltop. So how low is the ground from the hilltop? Can you guys see that? Great stuff. Okay, I know it looks weird, but remember, use your table. So okay, let me show you. Maybe for someone who was still lost, I want you to try to draw graphs. Okay, I want you to try to draw graphs. So on the next page, let me do this. Let me say on your table, say f of x equals negative 4,9 delta t square, and then g of x equals positive 4,9 delta t squared, and then start at 0 and at, let's say, 1, and then your step, let your step be 0, 1. Okay, let your step be 0, 1. Okay, and see what you will be getting. So you'll be getting x 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, and so forth until 1. And then you will be getting f of x is whatever, and then g of x is whatever. So you plot the values, you will then see that your f of x will be like this. Let me call it f of x. And then you will then realize that your g of x is like, let me change the color maybe. You will then realize that your g of x is like this. Right? Remember, g of x equals 4,9. It is smiling. F of x equals negative 4,9 x squared. If you plot, okay, let me not say, yeah, if you plot y versus x, okay, if you plot y versus x, okay, you will realize that your graphs are like this. And when you look at it, this is exactly what we found here. Can you guys see that? This is exactly what we found here. Okay, so we were looking at when the reference point is the hilltop. Okay, now let's look at when reference point when the reference point is the ground. I like saying, guys, remember the formula. Remember our formula was like this. Delta y equals vi delta t plus half a delta t squared. I like saying this is yf minus yi equals vi delta t plus half a delta t squared. So I like saying basically this is yf equals yi plus vi delta t plus half a delta t squared. Alright, I like saying this, and the reason I'm saying that is because I think this one here, maybe let me highlight it. This equation, I use it, this is me, I use it when they want a reference point to be the ground. So this will be y-intercept, but what is that y-intercept? This is the position or height of the cliff or building or whatever. Okay, this is height of the cliff or building or whatever, but where? Above ground. Okay, above ground. This is me. I like doing it in this way. Okay, I like doing it in this way. So now let's look at it. Now I'm going to now continue with what we've always been doing. When upwards is positive, when upwards is positive, and when downwards is positive, I want to show you how your graph looks like when your graph looks like when the ground is chosen as positive. So again, from the ground to the hilltop, you will agree with me that this means y is greater than 0. So your y-intercept is positive. Okay, y-intercept is positive. What is that y-intercept? This is the height of the building or hilltop above the ground. So here yi will be negative y because it is above the ground and going up. So since you're going up, you can't be saying it's positive, so it'll be negative, right? It'll be negative. So the graphs will be like these ones, but for this one here, I must move it up, and this part here must now touch the t-axis. Okay, it must now touch the t-axis. So let me show you what I mean. So it'll be like this. This is t-axis, this is y, so the graph will be like this. Okay, so this is y-intercept 0. So this is the time where it hits the ground. Can you see now? The ground is a reference. Can you see? Now let's try the other one. Look at how it looked like. Can you guys see how it looked like? But now, because the y-intercept is negative, the graph will have to go down, right? So it'll be like this. T-axis, y-axis 0. So it'll be like this. So what is this? This is your initial position. What is this? This is the height of the building or the hilltop from the ground. Right? Can you guys see that? This is how they look like. Okay? This is how they look like. So I like saying, remember what I said? I like saying this one will be y final would be y initial plus remember our initial velocity was 0, so it must be y initial plus 0 delta t plus half of negative 9,8 delta t squared. So this must be y initial minus 4,9 delta t squared. So obviously this one here must be y final must be y initial plus 4,9 4,9 delta t squared. If you can do what we did using the table form on your calculator, you'll be able to plot this thing. Okay, you will be able to plot this thing. Remember, you have t-axis, so you don't have to take negatives. T is never 0. T is never negative, so never take the negative part. So you will be getting something like this. Okay, you'll be getting something like this. I'm noting that you guys are doing mathematics, so I'm trying to show you how you got this. Okay, so I know someone is asking themselves, hey, can I find area of, hey, don't do that. Especially for grade 10, I mean, you grade 12. Because you're in high school, you don't do integration. So don't try to do anything. You can't really get any message on this graph in grade 12. Okay? All right. So this is all that you need. So you can find the height of your, you can find the height of your hilltop or your building on the graph. Here is it. It is the y-intercept. Okay. So now, let's then go to the next one. Let's go to the next one. I'm not going to cover the case where the object is thrown downwards. Okay. I'm going to cover here. I'm going to look at case 2. My case 2 here will be object is thrown upwards and returns. Okay, object is thrown upwards and returns. So the one where object is thrown downwards, you guys can try to do them on your own. I think you won't get it wrong. You will get it right. Otherwise, I will send you a working of it on your LMS. Okay. So now here, initial velocity is not equal to 0. Right? Initial velocity is not equal to 0. So what are we looking at? Here we're looking at, again, delta y is equal to vi delta t plus half a delta t squared. Okay? Now, we're going to start with a reference point being point of release. All right, a reference point being point of release. Let me see if I did that. Okay, point of release. Let me call it hilltop as well, not point of release. So hilltop or point of release, they are the same thing. Okay, so I'm gonna say hilltop. Yeah, let me stick to hilltop. So it'll be hilltop, i.e. point of release. Okay, it'll be point of release. So when upwards is positive and downwards is positive. Remember, this one here is one where we have time axis. If you remember from velocity versus time, this is where we have time symmetry. This is where we have time symmetry. Now, here, you expect your initial velocity to be positive. Obviously, your acceleration vector is negative 9,8. Here, your initial velocity will be negative and acceleration vector will be positive 9,8. So what do you have? You have delta y equals vi delta t minus 9,8 delta t squared. Remember, he is frowning. This one here, he is delta y equals vi delta t plus, oh boy, no. This is not 9,8. It was half. So this is minus 4,9. Right, this is minus 4,9. So this is plus 4,9. Remember, it is half a. All right. So somebody asks, why am I not using that yf equals yi plus vi delta t minus 4,9 whatever? I can still use it. However, with this one, because the reference is what is this? The top, the hilltop. I will say 0 plus vi delta t minus 4,9 delta t squared. Right? So what is this? This means so y is basically vi delta t minus 4,9 delta t squared. Okay, so in the same vein here, I basically say the same thing. Yf equals vi delta t minus 4,9 or plus 4,9 delta t squared, right? Okay, guys. Now, let's draw our graphs. Remember, I said there is time symmetry here. Okay, there is time symmetry here. So, remember, this side is upwards is positive. Now, if the object starts from y-intercept was 0, we saw that. If it starts from this point and it's a maximum, it'll always be like this, isn't it? It'll always be like this. So this is it. Now, this one here, it's smiling, right? Since it's smiling, it starts at 0, so y-axis, t-axis. So it'll be like this. Okay, it'll be like this. Okay, guys, can you guys see it now? Remember, when you are not sure, you use the equations that I showed you and you look at them like that. You solve them like that. Okay, so as you can see, it starts at y equals 0, it returns to y equals 0, right? It returns to y equals 0. Now, let's look at when a reference point is the ground. Let's look at when reference point is the ground. Remember what I had said. Here you will say, yf must be yi plus vi delta t plus half a delta t, right? So this means we will now have our graph will be its y-intercept will be where its y-intercept will be at, what is this, will be wherever. It will have a y-intercept which is not at 0, right? So we will then say, I remember we said, did we have initial velocity 0? Okay, I think I made a mistake. Object 2, object is thrown upwards. Okay, guys, I made a mistake here. Here, object is thrown upwards. Initial velocity, okay, was not 0. Yeah, initial velocity was not 0, so it's okay. But it's okay. Yeah, it's okay like this. Initial velocity was not 0, so I made, did I? Oh yes, initial velocity was not 0. Okay, I was right. Initial velocity was not 0, so I was right. Yeah, I was right. So it's okay. Okay, it's okay. I was right. Okay, now here, let's see what we have. Upwards is positive. Upwards is positive, and downwards is positive. Downwards is positive. Okay. So what we have, we still have upwards is positive. We still have initial velocity will be greater than 0. Acceleration vector will be negative 9.8. In the same way, so initial velocity is negative and acceleration is positive 9.8. So we have delta y equals vi delta t minus 9,8 delta t squared. It will be frowning. This one here, we will have delta y equals vi delta t, sorry, I forgot the square. Again, it is not, I don't know why I keep forgetting this. Half, so it will be 4,9. right, it'll be 4,9. So plus 4,9 delta t squared. Now somebody says, but you've been showing us yf yi, so this is similar to saying yi plus vi delta t minus 4,9 delta t squared, and this one is yf equals yi plus vi delta t plus 4,9 delta t squared. So with this one, what we're going to do, we know that our graph is frowning, but we said the ground is reference. Since we said the ground is reference, t-axis, y-axis. Now the graph will start at some point somewhere there, and then it'll reach maximum height and return. So this is the graph. Can you guys see that? This is your y-axis, the height above. Remember, this is the height above the ground. The hilltop is the height above the ground, and it returns to the same position. Can you guys see that? Good. Now the case where the graph is now okay, downwards is chosen as positive. Remember here, it smiles, right? It smiles, but this point is above the ground, right? So above the ground, this means you're going up, right? Because we said downwards is positive, so it'll be somewhere here, right? Now it'll be like this. Okay, it'll be like this. Okay guys, it'll be like this, and this is how we roll. Okay, it'll be like this, and this is how we roll. Can you see it's returning to the initial position? Okay, all right guys, now let's then try case 3. So case 3, this is where we say object is thrown upwards, returns, and passes initial point, right, and passes initial point to hit the ground, right, to hit the ground, right? So this is passes, okay, object is thrown upwards, returns, and passes initial point to hit the ground. Okay, so whoa, if you remember the case, it was case 4 on the velocity versus time. The arm where the graph was going to hit the ground was longer than when the object was going up, right? So again, initial velocity is not equal to 0, right? Initial velocity is not equal to 0. So maybe let me try to go back here, guys. Something that I want to tell you again here is that there is what we call time symmetry here, right? So if this is t1, this is t2. 0 to t1 is equal to t1 to t2. That's time symmetry. This point here is your maximum height, right? So t1, t2. 0 to t1 is equal to t1 to t2. In the same manner here, t1, t2, right? t1, t2. So time taken to reach maximum height, which is t1, is equal to time taken to return from maximum height to initial position. Okay, this is the time symmetry. Okay, so now this one, we're not going to waste much time, so we will say upwards is positive. Oh, sorry, let's choose reference point. Reference point in this case being hilltop or point of release, right? Hilltop or point of release, right? So hilltop or point of release. So now when upwards is positive, and then when downwards is positive. Okay. Now object is thrown upwards. Now since object is thrown upwards, it means initial velocity will be greater than 0. In the same way, yi will be greater than 0. But remember here, we're not necessarily looking at yi is greater than 0. We're not necessarily looking at yi because we say it's 0. It's returning to, no, it's not returning, is it? No, it's not returning. Yeah, it's passing the point, but we'll get there. So acceleration is negative 9,8. So here the reference point is the hilltop, right? The reference point is the hilltop. So here we have delta y equals vi delta t. Remember it was plus half, so it'll be minus 4,9 delta t squared. So here we have vi will be negative because downwards motion is positive. Acceleration vector will be positive 9,8. So delta y here will be vi delta t plus 4,9 delta t squared. However, this guy here, he is passing initial point. So this is him, this is him, this is him. Bah! Y-axis 0, t-axis, right? So this is time to reach maximum height. This is time to return to initial position, and then this is time to hit the ground. Okay, this is time that the object will hit the ground. Okay, all right. Now let's draw this one here. Remember, this graph is smiling while this one was frowning. Y-axis 0, t-axis. Remember this one? Again, time to reach maximum height, time to return to initial position, and time to, maybe let me call it F, and time to hit the ground. Okay, and time to hit the ground. Can you guys see that? Remember, this is maximum height. So guys, it's important to look at the shape of the graph. That will tell you which position was chosen to be, which direction was chosen to be positive. Okay, so this is how your graph looks like. Okay, remember here, this is when your reference point is the hill top or your point of release. Now let's look at when a reference point is the ground. Oh, lolo. So upwards is positive, and here downwards is positive. So we have it. Okay, so like we said, initial velocity will be greater than 0. A will be negative 9,8, and then here we will be saying initial velocity will be less than 0. A will be positive 9,8. This one, remember I said I like calling it y equals blah blah, right? I like calling it y minus yf equals vi, yf minus yi equals vi delta t plus half a delta t squared. Right, so let me just say, so this one will be yf equals yi plus vi delta t minus 4,9 delta t squared. This one here will be yf equals yi plus vi delta t plus 4,9 delta t squared. You expect this one to be frowning, you expect this one to be smiling. So let's see. The ground is reference. Now since the ground is reference, I like this one. This is where the object starts. Initial point, ground. Okay, remember T1, T2, and then a T final. Okay. Y-axis, T-axis. So it starts at, remember, initial velocity is 0, and not, this is not really this has nothing to do with initial velocity, but initial height, it is above the ground. Above the ground means you're going up, and we said going downwards is positive for us. So it'll start here and then come back and then hit the ground. So the time here is time to reach maximum height, time to return to initial position, and then time to hit the ground. Alright, and time to hit the ground. Okay, and time to hit the ground. Remember, this is yi. Remember what I said yi was? Yi was, okay, let me use a different color. Remember yi was hilltop, or top of the building, or whatever, right? Top of the building or hilltop. Okay, so guys, this is how you draw your position versus time graphs. Okay, this is how you draw your position versus time graphs. They are like this. Remember, the shape tells you which direction was positive, and the shape is, for a position versus time, you must remember half a is the coefficient of the delta t square. Alright, this is what will tell you if your graph is smiling, if it's smiling or frowning. Okay, so as you can see, this one here is height above the ground, height above the ground. This is maximum height above the point of release. This is maximum height above the ground. Remember, this is height above, maximum height above point of release, maximum height above ground. In the same way, maximum height above ground, height above ground. Okay, the hilltop or the top of the building, right? All right, guys, with that being said, we are done, and stay tuned for acceleration versus time and a summary of these diagrams, or of these graphs. So that's a wrap. See you next time.